So, yeah, so like Tom said, is volume good? Okay, so like Tom said, I did a little kind of tutorial on basic plotting stuff yesterday, and this is going to be some overlap, but I've tried to differentiate it. This is going to go through some of the basic plotting tools, and then talk about some of the newer burst plotting tools, and look at how you can visualize, just kind of some newer ways to visualize information in your radio that people should be aware of. And again, so this is our Virginia Tech building in Arlington. Another plug, we're hiring. If you haven't seen me a million times, we've said that already, but we'd love any SDR people. So okay, so I'm going to go through some radio visualization apps, talk about visualizing radio signals in streams, talk about how to trigger and deal with events that occur inside those streams, visualizing those events, and then talk a little bit more about kind of visualizing spatial data within radio applications. All right, so Gqrx, we'll just get this out of the way. So Gqrx is a tool that's often used. This is like a quick app you can go download and just kind of browse around the spectrum. So for visualizing and searching and seeing what's out there, this is a quick way to get started. I'm sure probably a lot of you have played with this before. So phosphor, also Sylvain's wonderful contribution and eye candy that I think we have running on just about every booth this year. And so I was going to just briefly show that. So phosphor is a OpenCL, OpenGL based tool that can really do very nice wideband visualization that you couldn't do just in software. So if I fire up MD radio, so a graph can be as simple as this. Basically, you can put a user source straight into your visualization sync. And what we're doing here is, so QTGUID provides these nice range widgets where I can put a range, or I can put a variable here called FC and a variable here called gain, and then plug those into the USRP block down here so that I can change the center frequency and the gain and runtime. So this is a quick way to do visualization. This is kind of like making your own little Gqrx live. So if we run this guy, this is the cell band right here. So we can look around, go for Wi-Fi. So this is a really quick and easy way to just start using your radio, looking at spectrum. The spectrograms in phosphor are like some of the best resolution. He's processing every single sample, and I'm not going to steal thunder. Sylvain's talking, I think, Thursday, which is going to be awesome. Yeah, so you'll see more phosphor. But you can't leave it out of visualization talk, because it's one of the best visualization tools we have. All right. So GNU also comes with these plotting tools for files, and so so streaming is useful if you're looking around and trying to look at things over the air, but often you're going to want to take a recording and look more at a static file on disk. So there's these tools that come with your radio, so like GR Spectrum, Plot C, and then finally that you can use to just look and scroll around inside a file and kind of inspect things without them flying by at a rate that you can't deal with. So this is a great thing for diagnostics and motor development, protocol analysis. All right. So in GRC, phosphor, as well as all of the graphical tools, are sitting over here. You can just search for GUI and it'll all come up. So I was going to go through, so I'm going to use this Z-Wave data set to go through some visualization examples. We're just going to kind of take, so it's the Z-Wave, if you're not familiar, is like the competitor for Zigbee. People are using it for, Internet of Things, little devices. There's like light bulbs that do Z-Wave and all kinds of random crap you might have around your house. It's going to have Z-Wave in it, apparently. And so Bill was kind enough to provide me with a data set, and that's just kind of what we're going to look at with some of these visualization tools, because it's kind of a fun problem. And it's a simple FSK kind of a waveform. All right, so this is a simple time plot of the signal coming in, and then this is a time plot where we're using some of the triggering features. So switch over to Gqrx. We can see that a lot of signals that you see over the air are going to be bursty. Right? That's kind of a common thing we see. Just read it. All right, so this is what we have. We can auto scale. This is a file we're playing back from disk. And so what we have here, we have spectrogram and a time plot. And we can see in the spectrogram that we have these bursts coming along every so often. And in the time plot, we kind of see every so often a burst comes along. But it's hard to look at. We'd like to just stop it, when that burst shows up. And so we have the triggering features now inside of Qt GUI. We turn on the control panel. We can turn our trigger on, set a level, delay if we want. And so here, now we're triggering on when these little Z-Wave FSK bursts come in. So this is great. Now we can actually look at it. If we want, we can zoom in and start looking at kind of like what does the ramp up for the signal look like, and what does the preamble for this look like. So we see it's kind of pretty oversampled FSK. And then we can also see the response coming back here. So this is either a response or another device that's more distant. So you can look at it. So those are kind of tools that they're just stuff you can do with normal Qt GUI plotters. So message-based plotters are something I've played around with a lot. So I have an out-of-tree repo called Gqrx. And so the idea here is instead of that kind of stream plotting, sometimes you've just got a message with a bunch of samples in it that you want to look at. And so like if I have like one received burst and I just want to look at the power of that chunk of samples, I can just plot that. And that's kind of, it's a message instead of the stream. It's really the whole difference. So I'd like to work to get these in tree, but they're out of tree for now, and they're all Python for now. So one of the cool things you can do with that is just plot random reads out of a file. So instead of trying to read or stream a whole sample file in, you can have now this message file source, which will seek to some offset, read in and samples, and then just throw them to this message plotter over here. And then we have basically this range widget where anytime you move the little range scroller back and forth, he's going to send a message to the file message source to read in a new chunk of data at a new offset, which will then send the message over to the plotter. So this is like a really simple message-based application for reading chunks of a file and plotting them kind of as an atomic message operation. So this is what it looks like. Here we have a scroll bar at the top where anytime we move it, it sends a message, and then that goes through, reads the chunk, and then sends it to these three plotters, which plot time frequency and a power, power over time profile of the signal. All right, so if I run that quickly, so let's do that on the Z-Wave data set. All right, so we can get samples. Somewhere we can find the first. INQ representation, our power over time, and then our PSD representation. So this is just another way to do file kind of analysis. All right. All right. So we can use that same kind of message-based plotting back to the Z-wave streaming example. So what I want to do here is, we saw how we could just trigger on the I and Q values rising over a certain value. So what we're going to do is, let's just extract a message every time that happens. Right? So if we put a time sync, actually there's already one there. So what we're going to do is we're going to take that raw I and Q and compute a magnitude squared value, and then just run it through a single tap IIR filter and do some smoothing on it. So if we look at that graph, we're basically creating a very simple detection metric for energy, right? So if we look at a bunch of samples, we start to see when a burst comes along, we get this detection metric that goes high, right? So this is a very simple energy-based detector. So if we stop this at some point, we zoom in, we look at the energy level down there. We can pick here, so like 0.001 looks like a reasonable triggering threshold that'll work for this example, right? So what I'm going to do is I'm going to put this trigger rising edge event block in and set a threshold here for 0.001. And say every time we rise over that threshold, we're going to extract 1,000 samples, 32 samples back from the rising edge, and we're going to debounce for 1,000 samples. So we won't detect another one for another 1,000 samples. So that's it. It's just going to, this is the same thing we were doing with the stream plotter trigger, except we're not plotting it, we're just extracting it and sending it off in a message. So that happens through these three blocks. This one triggers the event, this one extracts it, and then this one basically turns it into a message PDU. And so if we run this graph now, we want to look at this bottom here. All right, so we see these are asynchronous messages in the radio coming along. This is just, these are the actual samples, I and Q, you're seeing. And the message debug plot just prints them like text. So that's a way to see, that's one way to see messages. And apparently I should draw one more. Give it a second. So putting a lot of text on the screen is sometimes a problem. Anybody use GRC? All right. So if we send these to a message-based complex time plot, we should be able to look at the samples for each of these events. So here now, every time we pass this threshold, we're extracting these 1,000 samples, we're throwing them over this message plotter, and we're plotting them. So this is basically doing kind of the same thing as that stream trigger was, but now we have them in messages. So if we want to do some kind of a message operation on them, we can do that. So you've got kind of the same tools here. You can zoom in on the preamble, or however you want to use it. Do the same for a constellation plot. It's kind of cool. Talk to me in books. Without any sync, right? So we're not. Your next step would be to basically run this message worth of samples through some sort of synchronizer to start recovering whatever bits they're sending in the Z-Wave packet. All right. So that's a basic kind of a message-based plotting. So the last thing I want to show is using kind of that same message-based visualization architecture, but to do spatial visualization. So this graph I'm going to walk through just really quickly. So 88.1 is like the American University FM radio NPR station here in Washington, D.C. And their tower is probably like 2 miles that way. And so you can have a lot of fun with this. So what we're doing here is I have basically a stream of samples coming in from a USRP. And then here I'm doing a trigger which is not based on anything happening in the signal, because FM broadcast is just always on, right? The stream, it's not really an event thing. So but what I want to do is I want to just map kind of receive signal strength. So like if I'm WAMU, I might want to know my subscriber coverage. Where can people listen to my radio station and get good reception, right? Are there badly faded areas that I need to care about or not? So that's what we're doing here is we're basically, we're triggering every n samples and just extracting a chunk of raw IAQ. We're then just taking an average power over that message, probing the USRP GPS DO to get a NMEA location string, and then tagging that onto the message, and then passing it over here to write out to a JSON file. Right. So this down here at the bottom is an example of what a single record would look like. So we have a time in seconds. We have this GPS location, lat long, and an RSSI for the current signal strength of the FM that we're seeing. And so we write this out to a file. We have just this big list of observations that we've made of the broadcast station, and that's it. All right, so what's the thing? Obviously, you want to put this on your car and go drive around and just do some coverage mapping. So we did that, and you can parse the results, take this JSON, and then convert it into a Google Earth KNL file, and then you wind up with these wonderful plots of basically received signal strength spatially as you drive around. So this is kind of a cool way to do coverage mapping. So this is these are examples driving around DC here, and there's some kind of just cool propagation effects that you can clearly see when you do this. So like as you go up and over this bridge, you saw that signal strength climbed, and you have this great clear line of sight. And so signal strength is very high, and then once you go back down the ramp over here, you're going to start losing your loop again. Same thing here. This is actually driving right under DuPont Circle. You go through this tunnel here, and you can see kind of the RSSI drops, and then actually some of these are because of GPS loss, not because of signal strength loss. But regardless, you can kind of see the signal strength dipping as you go in. So it's cool to be able to visualize these sorts of radio effects. All right, so there's a few more. This is kind of the whole area. So this is Potomac coming through here, the Virginia side over here, and then DC over here. This is kind of driving up to where we are here. The broadcast tower is roughly around here. So you can see a lot of very strong measurements. And then our Q building is somewhere around here. So that's it. Just future work. Love to get this stuff into Qt GUI, move it all to C++, so we can kind of support stream and message-based plotters natively. Yeah, I'll talk more about. So one of the big dilemmas that comes up, and one of the focuses for this phosphor group is basically the idea that now if you have these messages flying around, you want to use things like fur filters and resamplers, things that already exist as stream blocks in your radio. But we don't want to have like two parallel sets of blocks, right, that are duplicitous. So we'd like to kind of come up with a good way to be able to instantiate those sorts of operations at either type of block, so we can, keep them both happy and interchangeable. So that's one of the things I'm interested in working on, and I think we're going to talk about more on Thursday at that working group. So thanks. Questions?
Yeah, we have time for one or two questions.
One of your posters outside, you use a raster plot to visualize the data. Is that a new visualization tool, or could you speak a little bit about that?
Yeah, so he asked about a raster plot for data. So yeah, GRQT GUI in the main radio has a stream raster plot where it just rasters data across. In fact, we can do it really quickly. And so PyQt has its own one, which it does the same thing, but it rasters a message at a time instead of a fixed number of samples. So if we put a time raster sync here, put it on the magnitude, for example. Call it 10. Alright, so it should be a coding names. Of course. Alright, so is there a file issue? Okay, well, we won't do that now. Yeah, but so there's a raster plot for both streams and messages.
He's running into a version issue with the plotting tool. QWT5 doesn't handle the computation power very well. QWT6 does, and we're trying to move away from QWT5 completely, but that's all that was. Okay, anything else? All right. Oh, there's a question back.
Hi, I'm just wondering, can you plot tags on the message-based, like time plots? Is that possible? And what about the scales? I noticed that we're running like scales on that time and frequency plots.
So you're saying like if you extract the message and then you want to know what tags were in that chart?
Right, like maybe you want to look at a time domain plot of like a Wi-Fi signal, but you want to tag it with maybe like the encoding or some other metadata that might be useful for you.
Right. So in here we have this. So there's the PMT structure, right, which is this polymorphic type. You can have any types in it. We have this kind of specialization of it called PDU, and PDU is just a tuple that has a chunk of samples and a dictionary. And so what we do is whenever you go through this block, it's going to take all the tags on the stream and put them into that dictionary. So it's going to, so that basically whenever you pass around these PDUs, there's a big dictionary there that can hold whatever you want to put on your message for you.
But I guess the question, so the visualization tool they show the PyQt plotter, is that, can you actually visualize those tags like you can in the Qt GUI?
Well, so there's no notion of like an offset anymore. There's just keys and values associated with the message. So you wouldn't necessarily like plot it like you would in a stream where it's like a little mark somewhere in the stream. I don't know, we haven't really thought about that too much. I think you could, when you do the message debug, it prints out that dictionary. So you get to see all the keys and values associated with that message. And then your block can kind of do whatever it wants to interoperate with them.
All right, thanks again, Tim.